oscillation of mass attached to a massless vertical spring. Okay, consider a spring, a massless spring, a spring constant K, and its length is L. It is hanged from a rigid support. Now, if I attach a mass M to the spring, it will be stretched downwards due to the weight of this mass mg, Fg, that is mg, in downward direction. Now suppose it is balanced. When it is balanced, there will be a restoring force or the spring force in upward direction. So in balanced state, this spring force will be some constant times stretch in the spring. Suppose this is stretched to y. Alright, and now if you see the weight in downward direction, this will be mg. Alright, this is the restoring or spring force in upward direction, and this is the weight in downward direction. So this spring force or restoring force is developed because of this weight. Alright, so what is the net force when this stretch is y naught? These forces Fs and Fg, the spring force and the weight, their sum is 0. They are balanced. The resultant of balanced force is 0. Alright, okay, Fs is minus k naught to y, Fg is mg, so it is 0, and you can see that ky naught will be equal to mg. Okay, now suppose if I apply some external force in downward direction. Now I apply some force in downward direction and stretch this coil or this spring in downward direction through y, and I let it go. What will happen? It will start oscillating. It will oscillate. If I stretch the mass attached to a spring downwards through y, or I compress this spring through y in upward direction, the restoring force comes into play, which is opposing my applied force. Take this at equilibrium position, pull it down through y, alright, or compress it up to y. Okay, so if I pull it downwards or compress it upwards through y and let it go, it will start oscillating. So this is simple harmonic motion. At this when this mass is attached or pulled down through y, suppose this mass is pulled through y from y naught, as you see in the figure, then new force will be F dash. This new force or new restoring force will be K times y naught plus y. The new restoring force developed in the coil will be minus K y naught plus y. But what will be the net force? Okay, so net force will be, alright, net force on the mass will be F dash minus F. F dash is a new restoring force at y, and F is the restoring force when it was in equilibrium state. So the force will be minus K y naught plus y minus K y naught, as the restoring force when it was in equilibrium, it is minus K y naught. Alright, the force will be now K y naught minus K y plus K y naught. So this will get cancelled. Then the force which will make it oscillate is minus K times y. Alright, As you know, the force is mass into acceleration. It is minus k times y. Then this acceleration will be minus k or m times y. Clearly, this acceleration is proportional to negative times y. So this is simple harmonic motion. This can be also written as minus omega square y, where omega square is k over m, or omega will be under root of k over m. Alright, so this is simple harmonic motion. The mass attached to vertical spring is given by this equation, as this is the simple harmonic motion. Now we can find this solution of this equation, as y represents should represent the periodic function. It represents the displacement of the mass at any instance of time, and the motion is periodic, so we must have the periodic solution for this. As this is the differential equation of second order, we can solve this by putting it, say y is a sine of omega t plus phi, or we can write it as y is a cos of omega t plus phi. These are the sine or cos functions are periodic, so they are the solution of this equation. Okay, let's first find the acceleration. So first find this velocity. All right, so by differentiating this equation, okay, so velocity will be, by differentiating this, it will be a omega cos of omega t plus phi. All right, again if we see, again differentiate it with respect to t to get the acceleration, it will be differentiation of cos of omega t will be minus sine, that it will be a omega sine of omega t plus phi, and differentiation of omega t will be omega. So y double dot is minus a omega square sine of omega t plus phi. All right, this will be written as omega square times a sine of omega t plus phi. This quantity is y. Here you see, so y double dot is minus omega square y. So this is the solution of the equation where omega, where a and phi are constants, arbitrary numbers or constant. So if you see the velocity of the particle, the acceleration of the particle, and the displacement of particle, each of these are the periodic, and we can draw the graph for these periodic functions. Thank you.